Welcome, dear listener, to a journey through the hidden corners of physics' earliest experiments, long before particle accelerators and quantum computers. Tonight, we step into the dimly lit workshops of the 19th century, where pioneers chased invisible forces with wires, glass. It is 6 o'clock in the morning. Outside, the sun is just beginning to rise over the treetops, but inside the workshop, Thomas Edison has been up for hours. His first task of the day is to siphon some sulfuric acid from a barrel using a hand pump. This is how it really started for those who worked at Thomas Edison's famous lab. The earliest employees were hired to help with experiments in his New York City shop. As Edison himself wrote in an 1872 letter, "I have men working for me in my shop that do not know what electricity is, or can tell you that a magnet has poles." He wanted to create something akin to a modern research institute, complete with scientists, technicians, and administrative staff. And while many people think of Edison as a great inventor, only one of his patents would be for something we would recognize as electrical today. The light bulb, more than anything else, was the product of his team's work, not Edison himself. This is partly why there are so few pictures of him working in the lab. There simply wasn't much for him to do. In fact, historians think Edison probably spent most of his time in the business office. But for those who did spend their days in the workshop, their jobs were often dangerous. For instance, when a new employee arrived, he was given a pair of rubber gloves to wear. These would protect him from electric shock, but they were already used and full of holes. At least they were better than nothing. Edison was convinced that silk gloves could be made conductive, so that a person could safely handle high-voltage wires. But the reality was that if an electrician got a shock, he would likely be killed, led to strange workplace behaviors like standing on a chair to get a better view of what was going on, because if you fell, you would spread the current out over a larger surface area and thus survive. In addition to electric shock, workers had to worry about burns, explosions, and even being crushed to death. Testing new equipment pushed the limits of what was possible. On December 1879, as electrician Francis Jensen put the finishing touches on an induction coil, it shot across the room and ignited a gas jet, blowing the coil up and throwing Jensen 30 feet through the air. While he did survive, this was not an uncommon occurrence in the lab. When a similar accident happened to another electrician, it was reported that his remains were found embedded in the brick wall of the building. When the lab moved to Menlo Park, New Jersey, things became even more cramped and dangerous. The main workshop was a converted barn. Sometimes they would get careless and fall down and get badly bruised. Even the simplest tasks could go wrong. Charles Brady King joined the lab at the age of 19, tasked with cleaning and labeling glassware. On one occasion, he picked up a beaker filled with hydrofluoric acid and set it down on a shelf where it was knocked over by another worker. The acid splashed onto his hands, and he tried to wipe it off. Since it was colorless and odorless, King didn't realize what had happened until it was too late. The pain was unbearable, and he screamed for help. No one came. The other workers knew that contact with the acid would burn the flesh right off your bones, so they simply stared at him, horrified. Finally, Edison arrived and pulled King from the beaker. But by then, the damage was done. His hands were burned all the way down to the bone. Doctors had to remove dead tissue every day for months as part of an experimental treatment, but his right hand was completely destroyed. Years later, He was awarded a government pension for his injuries. Not all of Edison's inventions were created equal. Some of his ideas were considered commercial failures, such as the alkaline storage battery. Each cell required a mixture of caustic soda and zinc. Mixing these two substances produced a lot of heat, and workers quickly nicknamed the process sweating. Imagine the worst case of heat rash you have ever had, then multiply that by 10. That was what the workers experienced. Their clothing would become soaked with sweat, and they would go home with their skin peeling off in sheets. But perhaps even worse than the physical dangers was the feeling that the work was never done. Edison demanded that the lab be fully stocked at all times. If a technician ran out of materials, he would have to leave his experiment and go purchase more supplies. He wasn't allowed to simply pop down to the corner store. Instead, he would need to take a horse and buggy to Newark, several miles away. Once he got there, he might find that the supplier didn't have what he needed. A bottle of acid, a handful of wire, or a box of batteries could be ordered, but it would take weeks to arrive. So the worker would have to wait until it turned up and then bring it back to the lab. If you were an electrician, the situation was even worse. Not only did you have to perform physically dangerous tasks, but you also had to be ready to respond to Edison's whims. According to one biographer, Edison would sometimes make you change a fuse in the middle of the night. Even after a 14-hour workday, you would be summoned to his house via an electric call button and would have to drop everything and come running. Today, we can see them almost anywhere, but they were once the product of countless failed experiments. In order to achieve this success, Edison employed a policy of ruthless efficiency. Technicians kept careful records of their experiments and findings, allowing them to reproduce results and improve processes. Each light bulb was marked with a number corresponding to its strength and longevity. If a particular type of filament proved weak and unreliable, technicians would immediately discard it and try a new approach. There were no formal scientific theories to test here. Rather, the goal was to solve a real-world problem as quickly as possible. To that end, Edison hired practical people who knew their way around machinery. After all, he famously said, "Genius is 1% inspiration and 99% perspiration." But for those who worked with him, it was more like 99% perspiration and 1% relief when you finally stopped working. Those who came to Edison expecting to advance scientific knowledge rather than invent marketable products were quickly disappointed. It was hard to conduct serious science in such a chaotic environment. Scientists who came to visit often complained about the mess and lack of organization. But it was this very chaos that allowed Edison to claim that his lab was the greatest workshop in the world. In 1882, he moved into a larger facility, but it was still far from ideal. Workers described it as a large room, surrounded by benches filled with all kinds of apparatus, connected with different parts of the building by cords and wires. The floor covered with shavings, broken glass, etc. Because he couldn't afford dedicated technicians, Edison asked his assistants to keep notes about experiments. But since they were also busy running errands and performing experiments themselves, those notes were often incomplete or inaccurate. Even so, it was enough to allow Edison to announce that he had invented the motion picture camera, the phonograph, and the first practical incandescent light bulb, among other devices. Some people were inspired by Edison's energy, while others simply thought he was lucky. In any event, despite the cramped quarters and danger, some of the best minds of the age were drawn to Edison's lab. Many of those who worked there went on to launch their own successful careers in science and industry. Maybe they were simply tired of working in Edison's shadow and wanted to forge their own path. Or maybe they saw how difficult it was to work in such dangerous conditions and decided to pursue less hazardous lines of work. Whatever the reason, the lab remained a dangerous place to work. And in 1884, one of the electricians was killed when he accidentally dropped a heavy coil of wire. At the funeral, Edison gave a speech in which he said, "A life so splendidly brave and true has left us, but has it really gone? Who can say that the good and true cannot live beyond the grave? For one so young to die thus is a calamity. Yet in his death he has done good service to the cause of electricity. He has fallen in harness and met death face to face in the service of science." Perhaps that was true. But behind closed doors, Edison admitted that it was difficult to replace skilled labor with unskilled. And when a replacement electrician came to him for his first assignment, Edison reportedly replied, "Go down to the receiving room and fetch out a box of electric buttons. Try and see how many different ways you can break the circuit." Then he added, "Make it lively." If you've ever worked in a modern physics lab, it's probably been a long time since you had to worry about glass blowing or getting mercury where it doesn't belong. But things were very different in the early days of physics, when scientists like Marie Curie, Albert Einstein, and Ernest Rutherford were making groundbreaking discoveries. Today, we're going to step back in time and explore what it was really like to work in an early physics lab. First, let's talk about glassware. Modern labs rely on plasticware for many applications, but in the late 19th and early 20th centuries, glass was the way to go. And not just any glass would do. These scientists were dealing with corrosive acids, bases, and solvents that required special glassware. So each piece was carefully selected based on its chemical resistance. Glassware came in all shapes and sizes. There were round bottom flasks for reactions, pipettes for transferring liquids, crucibles for heating substances, and beakers for mixing. Sometimes they'd even color code the glassware depending on its use. The glassware was so important that there were entire workshops dedicated to making and repairing it. But even with the best glassware, accidents could happen. Imagine a beaker falling off a shelf and shattering on the floor. Not only would that be a waste of expensive equipment, but it would also release dangerous chemicals into the air. That's why glassware was often stored in special cabinets that kept them out of reach. But sometimes the glassware wasn't the only thing that could break. Our next hazard takes us back to the early 20th century, when World War I was raging in Europe. Many scientists put their research on hold and joined the war effort. This meant that some labs were left without their usual staff, leading to a shortage of trained personnel. But it wasn't just the people who were in short supply. Glassware, chemicals, and equipment were also hard to come by. This created a unique set of challenges for those who did continue working. For example, researchers had to make do with whatever materials they could find. They might have to use old or damaged equipment, or find creative ways to make up for the lack of certain chemicals. This meant that experiments were often more difficult and time-consuming, but it also led to some innovative thinking. Scientists had to learn how to troubleshoot problems and make the most of limited resources. In some cases, they made significant discoveries despite the challenges they faced. However, this wasn't always possible. Many labs were forced to scale back their research or even shut down completely. this had a major impact on the progress of science during the war years. With fewer people working on important problems, it took longer to make breakthroughs and solve mysteries. In addition to the practical challenges, there was also a heavy emotional toll. Many scientists were torn between their duty to their country and their desire to contribute to knowledge. Ultimately, this was a time of great sacrifice and resilience in the world of science. Those who persevered helped to ensure that the pursuit of knowledge would continue despite the turmoil of war. Now, let's move on to our next topic, Mercurys Danger. Back in the early days of physics, scientists didn't know much about the harmful effects of mercury. They used it for all sorts of things, from making electrical contacts to coating glass to create barometers. But today, we know better. Mercury is toxic and can cause serious health problems if inhaled or touched. That's why we don't use it as much anymore. But back then, safety wasn't really a concern. Scientists would just open up a vial of mercury and start using it right away. They didn't have any special equipment to prevent spills or leaks. So if they accidentally knocked over a vial, mercury would spread everywhere. And since it's so dense, it would be hard to clean up. But it wasn't just the physical danger that worried scientists. They also knew that mercury could react with certain substances, creating hazardous compounds. For example, if mercury came into contact with acids, it could release poisonous gases. Despite these risks, scientists still used mercury because it had some unique properties that were useful for their experiments. For example, it's a great conductor of electricity, so it was perfect for making batteries. It's also very dense, so it was useful for weighting objects. But as time went on, scientists started to realize that the risks of using mercury outweighed its benefits. In the early 1970s, the Environmental Protection Agency banned the use of mercury in most laboratory settings, and today, we're much more careful about how we handle this dangerous substance. If we do need to use it, we take special precautions to prevent spills and leaks. We also use equipment like fume hoods to keep the mercury vapor from building up in the lab. It's a shame that we can't just use mercury freely like we used to. It's a fascinating substance with a lot of interesting properties, but it's just not worth the risk to our health and safety. Now let's shift gears and talk about something that illuminated the lives of early scientists, arc lamps. These lamps were invented in the 1800s and were a popular source of light in labs and factories. They worked by creating an electric arc between two electrodes, which produced a bright light that was perfect for illuminating large areas. One of the first famous examples of an arc lamp was the one used by Thomas Edison to inaugurate his first commercial electric lighting system in 1882. These lamps were popular for several reasons. First, they were bright and efficient, producing around 2,000 lumens of light with just 160 watts of power. Second, they were relatively cheap to produce, costing only about $5 in today's money. And third, they were easy to maintain, requiring little upkeep to keep them in good condition. However, they weren't without their drawbacks. Arc lamps were noisy, emitting a loud humming sound that could be annoying and disruptive. They also produced a lot of heat, making them a potential fire hazard. And finally, they were big and bulky, making them difficult to move around. Despite these drawbacks, arc lamps were widely used for decades, eventually being replaced by newer, more efficient technologies, such as fluorescent lighting. Today, arc lamps are still used in some specialized applications, such as in movie theaters and welding. They re a reminder of an important era in lighting history and a testament to the ingenuity of the engineers and inventors who created them. Let us turn our attention to a place where the lights were kept low and the atmosphere was thick with anticipation, the dark room. This dimly lit room was an essential part of any early physics lab, and it played a crucial role in various experiments. The primary purpose of the darkroom was to develop and print photographs. In the early days of photography, this process required a lot of manual labor and expertise. First, the film had to be loaded into a large camera and exposed to light for a specific amount of time. Then it had to be removed and placed in a developing solution to create the image. Finally, the image had to be fixed in a special solution to prevent it from being further affected by light. All of this had to be done in complete darkness, which is why the darkroom was kept so dim. But the darkroom wasn't just used for photography. It was also an important tool for making scientific measurements. For example, physicists would use special cameras to capture images of particles that were invisible to the naked eye. By studying these images, they could learn more about the nature of light and matter. The darkroom was also used for spectroscopy, a technique used to analyze the composition of materials. By shining light through a sample and examining the resulting spectrum, scientists could identify the elements present in the material. In addition to these scientific uses, the darkroom was also a place of creativity. Many scientists enjoyed the artistic process of making photographs, and some even experimented with different techniques to create unique effects. Overall, the darkroom was an integral part of the early physics lab, providing the tools necessary for capturing images, making measurements, and advancing our understanding of the physical world. Let's start out with a nice, quiet day in the office. It's 1897, and you're working for a famous physicist. You've been tasked with a simple job. See if you can detect these mysterious rays that have been coming from some mineral samples that your boss found down in a South African mine. Your boss has been busy, but he left you this fancy new device to play with. A device with tubes and wires and glass spheres. Hey, maybe even a cathode ray tube. Pretty neat. You turn on the high voltage power supply and nothing happens. What? Check the tubes. Okay, they're all good. Make sure the wires are connected. Yeah, that's not the problem. Wait a minute, those mineral samples, maybe it's them. Put them close to the detector and whoa, there's a big flash and then a shower of sparks. That's strange. It almost looks like lightning, but it's inside this box. Turn off the power, take out the samples, watch it closely. Is it doing it again? No, it's totally silent now. So maybe it's those mysterious rays. Put the samples back in the box and repeat the experiment. It works. You might be on to something here, but something doesn't seem right. This doesn't look natural. You try different things, and it seems like no matter what you do, if you put the samples in the box, they immediately start sparking and flashing like fireworks. Maybe this isn't radiation at all. Maybe it's something else. Put the samples away and go back to the desk. Time to think. Maybe it's not radiation, but how can you test for that? How do you know what you don't know? Well, first of all, it's probably not magnetism because you've tested that. Then it probably isn't sound because you couldn't hear anything when it wasn't doing that. Also, you didn't feel anything when it wasn't doing that either. Perhaps it's light. You'd never noticed before because you always had the box closed. But you've recently learned that light can do more than just illuminate objects. Let's check it out. leave the box open and shine a bright light into it. Nothing. Close the box and shine a bright light into it. Whoa, there's a big flash and then a shower of sparks. It's just like when you put the samples in. But why? Why does the box make a difference? If this is light, why does closing the box affect the amount of light? That's weird. Think about it some more. Is this like radio waves? Radio waves travel through the air, but they need to be contained somehow. They can't just travel in all directions. Maybe they need a wire to travel along. Try wrapping a wire around the box and connecting it to your power supply. Can't hurt. It already does weird things with the light. What's another experiment you can do to find out more? Well, you could see if the sparks jump across a gap. Take out the samples and wrap some insulated wire around the box, connecting it to your power supply. Carefully touch the two ends of the wire together. Sparks fly. Cool. Then pull them apart slowly. Sparks keep flying. Pull them apart quickly. No sparks. Too far. No sparks. Bring them closer together. Sparks fly again. Fascinating. And since we're getting so fancy, why not make a bigger gap? Wrap the wire around the entire box, connect it to the power supply, and touch the two loose ends together. Nice arc. Pull them apart slowly. Still going. Pull them apart quickly. Nothing. Too far. No sparks. Bring them closer together. Still nothing. These aren't like normal electric sparks. If they aren't radiation, light, or magnetic fields, what the heck are they? Are they some kind of particle? Could they be X-rays? Well, X-rays were discovered in 1895, only 2 years ago, and they do interact with matter in similar ways. But you would have seen evidence of them by now, wouldn't you? You know what else was discovered only 2 years ago? If this were radioactivity, these mysterious rays would be coming from the samples themselves. Maybe you should ask your boss about this. But then again, he's kind of flaky. Remember how he went missing for weeks last year after claiming he was going to visit a famous scientist? Yeah, turns out he was spending all his time at sea, chasing mythical radioactive waves. He was even trying to build a device to detect them. When he came back empty-handed, everyone at the Institute was pretty disappointed. Well, except for you. While everyone else was busy arguing with your boss about the merits of radioactive waves, you took the opportunity to set up your own little shop in the basement. You learned a lot about electricity, magnetism, and radio, while everyone else was distracted. You also learned how to read blueprints, mostly by trial and error. When your boss showed up in the basement asking for the device you built him, you told him you weren't quite finished yet. He got mad, but you did uncare, because you knew that one day your hard work would pay off, and then he would see, hey, come back here. You haven't paid me for that device yet. Fine, here's the device you asked for. You can pay me afterwards. Did you say device? What happened to my device? What did you do with it? I wanted to test those mysterious rays. You never gave me any money anyway. Then you spent the next few months improving your setup, testing everything you could think of. And now you're ready. Time to conduct your own experiments and make your own discoveries. What will you discover? Watch next time to find out. Actually, don't bother. You'll probably die. Working in an early physics lab was dangerous. Just ask Nikola Tesla. In 1899, Tesla was working on a large induction coil to generate high-voltage electricity for his new X-ray machine. High-voltage electricity is dangerous, but Tesla figured he'd be safe enough in his well-insulated laboratory. On the other hand, He was known for skipping safety precautions sometimes, like when he famously stuck his hand in a high-voltage Tesla coil, shocking himself badly. But this time, things were different. While working with the large induction coil, Tesla grabbed some nearby metal bars and started waving them around. The metal bars were connected to the high-voltage coil, and Tesla accidentally caused a large electrical arc to form between them, burning his hand badly. Had it not been for his assistant, who jumped in just in the nick of time and pushed the metal bars away from him, Tesla likely would have been killed. His hand was burned so badly that it was impossible to rewrap the bandages, and the infection eventually spread to his arm. Doctors gave him an option: cut off your hand or die. Tesla chose amputation. Let's hope you don't end up in the hospital for too long. After all, there's a lot of important things happening in physics right now. Ernest Rutherford is working on his gold foil experiment. Max Planck is trying to figure out how light works, and J.J. Thomson is searching for the electron. You'd hate to miss any of that, would you? Oh, hey, you're back from the hospital. Welcome back to the lab. I'm working on something really cool. I've managed to design a device that can measure the size of atoms. It's not perfect yet. I still need to calibrate it, but it's really coming along. Come over here and take a look. Oh great. Looks like you've got yourself a Nobel Prize. Actually, it's not that cool. I didn't get it to work. Matter of fact, it doesn't even look anything like the real thing. Yeah, me neither. But you know, at least I tried. When you work in physics, it's often difficult to make progress without funding. For instance, how much do you think it cost to produce the first crude oil light bulb? About $100,000 in today's money. Yet once Thomas Edison developed the first incandescent light bulb in 1879, it only cost $2 to mass produce. With funding, it becomes much easier to scale up your ideas from a rough prototype to a finished product. So where does the funding come from? Well, often it comes from wealthy individuals or families. For instance, the Cavendish Laboratory at Cambridge University was founded with a donation from the family of a famous scientist. Or take the example of the Rockefeller Institute, which was founded with a $1 million donation from Rich Dude. Without such donations, many scientists would struggle to receive adequate funding for their work. Most people have no idea how hard it was to work in an early physics lab. Just imagine being surrounded by equipment that you yourself built, being pushed to your physical and mental limits, and having a great appreciation for how difficult it was to discover the laws of our universe. First, there was the ritual of record keeping. For many scientists, the process of recording their data is almost meditative. In fact, we might even go as far as to say that without the meditative process of recording data, science as we know it would not exist. Without the practice of meticulous record-keeping, all the great discoveries made in the past would have been lost forever. In the early days of physics, before computers were invented, the only way to keep track of experiments was by hand. This required a great deal of concentration and focus. And just as today, when scientists are expected to publish their findings, they were expected to present their work to a group of peers. These presentations often took the form of papers which had to be written in Latin, since that was the common language of scholarship at the time. The papers would then be read at a meeting of the Royal Society or some other learned body. If the paper was accepted, it would be published in a scientific journal. All of this added a great deal of pressure to the scientists working in the labs. They knew that their work would be scrutinized by their peers, so they had to make sure that their data was as accurate as possible. But despite all of this, There is something strangely calming about the process of recording data by hand. It allows the scientist to reflect on their work and to appreciate the beauty of the universe. It is a time for quiet contemplation, and it is an essential part of the scientific method. However, while the actual writing up of results was important, it was only half the battle. The other half was making sure that the experiment itself was valid. This required a great deal of preparation and planning. Before conducting an experiment, scientists had to make sure that all of their equipment was in good working order. They also had to develop a clear hypothesis and experimental design. Once the experiment was underway, scientists had to be extremely careful to avoid contamination or other errors. And finally, they had to be prepared to analyze their results and draw conclusions. All of this required a great deal of time and effort, but it was all worthwhile when a discovery was made. Speaking of which, now let's move on to the next point: intermittent breaks. Physics is a very challenging field, and those who work in it are often under a lot of pressure to produce results. Whether it's from funding agencies, from their employers, or from themselves, physicists are constantly feeling the need to push forward. However, it's important to remember that groundbreaking discoveries don't just happen overnight. Sometimes they can take years or even decades to make. One of the best things you can do as a physicist is to take intermittent breaks and to allow yourself the time to think. This doesn't mean that you should stop working altogether, but rather that you should take some time away from your current project and focus on something else. Maybe it's time to start that personal project you've been meaning to work on, or to catch up with some old friends. Taking a break can also help you to get a fresh perspective on your work. When you come back to it after some time away, you may be able to see new possibilities or solutions that you weren't able to see before. Of course, this isn't easy to do. It's often difficult to take time away from your work, especially when you feel like you're behind on your schedule. But it's important to remember that taking a break is not only okay, it's sometimes necessary. And speaking of taking a break, let's talk about nighttime isolation. One of the most difficult parts of working in an early physics lab was the nighttime isolation. Most of these labs were located in remote areas, away from the noise and distractions of civilization. This was so that the scientists could focus on their work and make breakthroughs without interruption. However, it also meant that they were often completely alone at night. This could be very difficult, especially if the scientist was working on a particularly challenging problem. There was no one to talk to or bounce ideas off of, and this could lead to a lot of frustration. Additionally, the lack of company could be quite lonely, and it often led to homesickness. Many scientists working in these early labs were young men who had left their families and friends to pursue their work. They could often be found writing letters to their loved ones, pouring out their hearts, and sharing their hopes and dreams. Despite the difficulties, though, most scientists wouldn't trade it for the world. They knew that they were making discoveries that could change the world and that made all the hard work worthwhile. Finally, let's discuss the vision of the future. Working in an early physics lab was tough. The hours were long, the pay was low, and the competition was fierce. But despite all of these challenges, the physicists of this era were driven by a single-minded vision of the future. They saw a world that was transformed by their discoveries, a world where the laws of nature were understood and harnessed to improve the lives of everyone. This vision kept them going when times were tough and inspired them to make some of the greatest discoveries in history. Today, we live in a world that is truly transformed by physics. We have technologies that were once thought to be impossible, and we have a deep understanding of the universe that our ancestors would have never believed possible. This is the legacy of the early physicists, and it is a vision that continues to inspire us today. So what do you think? How do you think scientists manage to make such big discoveries? And what kind of challenges do you think they face in their day-to-day work? Maxwell was a child of 5 when he moved to Edinburgh in 1831 with his mother and 2 siblings. His father had died 3 years earlier, and his mother took up residence at a lodging house at No. for George Square. Like many other famous scientists before and after him, Maxwell would take long, solitary walks around the city. He was particularly fond of wandering around the area of Caltane Hill, where he would contemplate the mystery of the universe. It was during these early years that Maxwell developed his lifelong passion for geometry. He would spend hours making farms of soap bubbles, seeing them as an analogy for the nature of reality. In his mind, the film of soap stretched between the wire frames represented the surface of the earth, while the air trapped inside the bubbles represented light or even matter itself. This game of bubble farming led Maxwell to discover one of his most famous properties of electromagnetic waves. As any bubble farmer knows, if you blow a bubble at just the right angle, it will split into 2 identical bubbles, each with half the volume of the original. But if you do this twice, you'll end up with 4 bubbles, each with 1/4 of the volume of the original. And if you do it 3 times, you'll get 8 bubbles, each with 1/8 of the volume. Each time, the number of bubbles doubles, while their individual volumes halve. What's going on here, you might ask? Well, Maxwell noticed that the total volume of the bubbles remained constant, which made him wonder if electromagnetic waves, like light, also came in discrete packets. This discovery would later lead to the development of quantum mechanics, but that's a story for another time. When Maxwell was 8 years old, his mother hired a private tutor named John to help him with his education. However, it soon became clear that Maxwell had little interest in what was being taught in his school. Instead, he preferred to study on his own by reading books from his father's library. At this point, Maxwell's interests were very broad, ranging from mathematics and astronomy to chemistry and optics. But as he grew older, he began to focus more and more on mathematics. By the time he was 12, he was already working on advanced mathematical problems that were beyond the scope of most university courses. In 1841, Maxwell entered the University of Edinburgh at the age of 14 to study both mathematics and natural philosophy, the Scottish term for physics. Maxwell excelled in his studies and graduated with first-class honors in both subjects. His academic record was actually so impressive that it drew the attention of the faculty, who awarded him a prestigious fellowship to study at the Cavendish Laboratory at Cambridge University in England. So, at the age of 19, Maxwell left Edinburgh to begin his graduate studies at Cambridge. Unfortunately, Maxwell's time at Cambridge was not all smooth sailing. He struggled with bouts of depression and ill health, likely due to undiagnosed bipolar disorder, which made it difficult for him to focus on his work. Additionally, the mathematical standards at Cambridge at the time were quite low compared to those of today, and this frustrated Maxwell, who was already a brilliant mathematician. To make matters worse, there was a growing tension in the department between the old guard, led by William Hopkins, and the new guard, led by Maxwell's supervisor, William Clerk Maxwell, and his peers, felt that Hopkins and his colleagues were holding them to a different standard because they did not like the new teaching methods being employed by Clerk. This tension reached a boiling point when Hopkins accused Maxwell of cheating on an exam. Maxwell, who had always been rather introverted, became extremely upset and stopped speaking to Hopkins and anyone else from the old guard. Though he was cleared of any wrongdoing and went on to win several prizes for his mathematical abilities. This experience left a deep scar on Maxwell's psyche. Feeling alienated and unwell, Maxwell spent most of his time alone, walking the streets of Cambridge or exploring the nearby countryside. It was during these solitary walks that he made some of his most important discoveries. For example, he realized that a moving electric charge would create a magnetic field, and that a changing magnetic field would create an electric current. These insights would later be incorporated into his famous theory of electromagnetism, which unified electricity, magnetism, and light. But at the time, Maxwell kept these ideas to himself, knowing that his colleagues would not understand them. Instead, he turned his attention to solving problems in other areas of mathematics. After completing his graduate studies in 1846, Maxwell returned to Edinburgh as a professor of natural philosophy at the University of Edinburgh at the age of 25. Despite his young age, Maxwell was already considered to be one of the leading experts in the field of optics. In fact, he was invited to give a series of lectures at the Royal Institution in London on the topic of color. During these lectures, Maxwell presented his groundbreaking work on colorimetry, which showed that any color could be produced by combining three primary colors in different proportions. He also demonstrated his famous color wheel, which is still used by artists and designers today to mix colors. However, not everyone was impressed by Maxwell's work. One of his colleagues at the Royal Institution, the physicist John Henry Pepper, was particularly skeptical of Maxwell's ideas. Pepper believed that the mixing of colors should be done by hand, and he was concerned that Maxwell's color wheel would make people lazy. In addition to his professional troubles, Maxwell's personal life was also in turmoil. He had become engaged to the daughter of a wealthy landowner named Catherine Campbell, but the engagement was broken off after Maxwell suffered a psychotic episode in which he talked for 58 hours without stopping. This episode, along with other symptoms such as delusions and hallucinations, convinced Maxwell's friends that he needed to be kept under close watch. They pressured his mother to hire a full-time servant for him and encouraged her to keep him away from dangerous chemicals and sharp objects. Maxwell, who had always been sensitive about his mental health, was deeply humiliated by the arrangement and saw it as a sign of weakness. Despite these setbacks, Maxwell continued to make important contributions to the field of optics. In 1855, he discovered that the speed of light in a medium is inversely proportional to the square root of its refractive index. This discovery, known as Maxwell's equation, was a key step towards the development of Einstein's theory of special relativity. Maxwell also worked on developing the first color photograph and made significant advances in the understanding of molecular motion. However, as Maxwell's career progressed, it became increasingly clear that his peers did not fully appreciate the significance of his work. They often dismissed his ideas as being too speculative or theoretical and failed to recognize the originality of his thinking. In particular, Maxwell's attempts to unify electricity and magnetism were met with skepticism. as most scientists at the time considered these to be separate phenomena. Even Maxwell's friends and family doubted his ability to succeed in such a highly competitive field. Despite these doubts, Maxwell continued to pursue his research on electromagnetism. In 1861, he published a paper on the subject, but it received little attention from the scientific community. Maxwell then decided to take a break from his research and move to Belfast, Ireland, where he became the secretary of the Royal Irish Academy. In Belfast, Maxwell enjoyed a more relaxed pace of life and was able to reconnect with his friends and family. He also had the opportunity to travel around Europe, where he met many other scientists and learned about the latest developments in their fields. During his travels, Maxwell visited Paris, where he saw a demonstration of a new invention called a kaleidoscope. This device used mirrors to reflect and magnify an image, creating a kaleidoscope-like effect. Maxwell was fascinated by the invention and began to wonder if it could be improved. Back in Belfast, he started experimenting with different ways to improve the design of the kaleidoscope, and in 1862, he published a paper on his findings. The paper was well received by the scientific community, and Maxwell began to gain a reputation as a leading expert in the field of optics. It seemed as though Maxwell's career was finally on the upswing, but tragedy struck once again when his wife, who had been suffering from depression and possibly bipolar disorder, took her own life. Maxwell was devastated by the loss and withdrew from society, throwing himself into his work. Just a few months later, Maxwell was offered a position at the Cavendish Laboratory, which was being headed by his former supervisor, William Clerk, who had succeeded Hopkins. Upon hearing this news, Maxwell immediately packed his things and moved to Cambridge, where he would spend the rest of his career. At Cavendish, Maxwell and his colleagues made great strides in our understanding of electricity and magnetism. They discovered the laws of electrodynamics and showed that electromagnetic waves could travel through a vacuum. In 1865, Maxwell published his famous set of equations, which described the relationship between electricity and magnetism. These equations are now known as Maxwells S Equations and are considered to be one of the most important scientific discoveries of the 19th century. They provided the theoretical foundation for the development of many new technologies, including radio, television, and radar. Sadly, Maxwell would never live to see the impact of his work. He died of a heart attack in 1879 at the age of 68, but his legacy lived on through his students and colleagues. Many of Maxwell's students went on to become famous scientists in their own right, including J.J. Thomson, who discovered the electron, and Ernest Rutherford, who discovered the atomic nucleus. Meanwhile, Maxwell's colleagues built on his work to develop the first practical applications of electromagnetism. These applications revolutionized the way we communicate, travel, and think about the world around us. Today, Maxwell's work is remembered through numerous awards and scholarships that bear his name. His story is an important reminder that sometimes genius comes at a price, and that even the greatest minds need support and understanding. What if I told you that all light is made of ripples in a single field, that it's all connected, that it's all the same stuff? You probably wouldn't believe me, but that's exactly what James Clerk Maxwell discovered. And all he needed was a bit of marriage, some ribbon, a magic box, and a whole lot of math. In 1865, physicists knew there were two ways to make waves. You could disturb a rope or push a child on a swing, but when it came to light, they had no idea how to make it. Michael Faraday, one of the most famous scientists of the time, was fond of showing off his spectacular demos where he would use a battery and a spinning disk to generate light by hand. It was fun to watch, but no one could figure out what was going on. Then along came Maxwell. He came up with a set of equations that described not just how light could be generated, but also how it travels through space and time. And it turns out that light is just one kind of wave in a whole sea of electromagnetic radiation. Thanks to Maxwell, we know that all light is made of ripples in a single field. It's all connected. It's all the same stuff. The only question is, why doesn't everyone know about him? Well, here's his story. Maxwell was born in Edinburgh in 1831. His mother was a strict but loving woman who ran a school for young ladies. When she died, his father sent him to the prestigious Edinburgh Academy, where his peers were mostly sons of the wealthy elite. It was an environment that Maxwell thrived in. He was great at math and science, especially physics. But when he got to university, he didn't have it so easy. Like many other Scottish universities, the University of Edinburgh was pretty poor. So when Maxwell arrived in 1847, it only had one chair of natural philosophy, which is what physics was called back then. And it was held by a grumpy old man named William. As soon as Maxwell started attending his lectures, he realized something was wrong. All the professor did was drone on about Newtonian physics, which Maxwell already knew backwards and forwards. And that wasn't all. The professor seemed downright hostile to the concept of doing your own research. There are two things I would never attempt, the professor once told the class: to repeat an experiment from a reputable source and to repeat an experiment of my own design. Fortunately, Maxwell found plenty of opportunity to do both. At home, he repeated experiments from reputable sources like this one by French physicist Louis Bigot. By placing two magnets at the poles of a suspended bar magnet, he managed to balance it perfectly in mid-air. This showed that magnetic repulsion can balance magnetic attraction. If you arrange the magnets properly, the next step was to repeat the experiment in 3D, which ended up looking like this. Maxwell published his results in the local philosophical journal and got some nice comments from a scientist at the Royal Observatory named John Herschel. As Maxwell began sending more of his work to Herschel for feedback, their relationship became more like a scientific mentorship. With Herschel's encouragement, Maxwell went on to publish over 60 papers while still an undergraduate. But unfortunately, the chair of natural philosophy remained stubbornly stuck in the past. So, after getting his degree, Maxwell decided to go to the future, specifically London, where the most exciting research was being done. There, he got a job as an assistant in the Royal Observatory, which meant he could spend his days studying astronomy and his nights thinking about anything he wanted. The next 4 years were a whirlwind of activity. Not only did he manage to get his own research out, but he also had enough free time to fall in love, marry, and have children. Life was good. Then, in 1856, the chair of natural philosophy at the University of Edinburgh retired, and Maxwell got the job. Now he had the freedom to hire his own assistants and start his own research group. Within a year, he had 3 chairs, including one in natural philosophy, which finally allowed him to focus on his work instead of his day job. Now let's talk about those 5 equations. Each one describes a fundamental property of electromagnetism. We'll take them one at a time and try to understand what they mean. No. One says that electric charges don't accumulate. Any excess charge flows into the ground and dissipates. No. 2 says that if you have a changing magnetic field, then you must also have an electric field. In other words, magnetic fields can change the behavior of charged particles. No. 3 says that if you have a changing electric field, then you must also have a magnetic field. No. 4 says that magnetic poles come in pairs. You can never isolate a single one in free space. And number 5 says that electric charges only experience forces if they are moving relative to the magnetic field. These may seem like niche observations, but together they reveal something extraordinary. Changing electric fields make magnetic fields, and changing magnetic fields make electric fields. The two types of fields are coupled together. They influence each other. And since everything is made of charged particles, all you need to make a wave is a wiggle in one field, which will make a wiggle in the other. It's like pushing a child on a swing or disturbing a rope. Just one wiggle is all it takes. But now you might be wondering, why doesn't this explain how light works? Well, Maxwell's genius was realizing that these equations also predicted new kinds of waves, ones that could travel through a vacuum. It turned out that the speed of these waves depended only on the properties of the fields themselves, not on whatever medium they were traveling through. And when Maxwell plugged in the known values for electric and magnetic fields, he found that the speed of the waves came out to be exactly the same as the speed of light. This was the first inkling that light might be an electromagnetic wave. But to confirm it, he needed to show that these waves could move through space as well as time, and that required a piece of ribbon. When Maxwell was working on his equations, there was no such thing as a computer. So he did most of his math by hand, which was luckily a habit he picked up from his father. But even so, checking his derivation for errors took a Herculean effort. His wife, who was acting as his research assistant, spent weeks meticulously copying down every step. Then one night, she noticed that something wasn't right. One of the terms didn't cancel out the way it was supposed to. It was a lucky mistake, because it meant that Maxwell had left out a factor of c, the speed of light, in his final equation. Once that was corrected, everything fell into place. The term that didn't cancel out suddenly did, and the result was beautiful. It showed that the electric and magnetic fields could combine to form a single vector quantity that had both a magnitude and a direction. And if you take the curl of that, you end up with another vector that's the same as the original, except for a minus sign. Curl of a curl always has a minus. Curl is basically a mathematical operator that tells you how much a vector field twists on itself. So this equation says that the twist of an electromagnetic wave points in a direction perpendicular to the wave itself. And this perpendicular direction changes as the wave wiggles up and down. That means an electromagnetic wave must be a transverse wave. The charges in the wires of the telegraph cables that connected London and Edinburgh were vibrating perpendicular to the direction that the signals traveled. That's a mouthful, I know, but it also means we can predict what happens when light interacts with matter. For instance, the electrons in an atom absorb the changing magnetic field of a wave and then re-emit it in a slightly different direction. This causes the light to scatter in all directions, which is why the sky is blue. Maxwell's equations also explained how a changing electric field could make a magnetic field, which inspired Heinrich Hertz to invent the spark gap, which generated radio waves. It was the discovery of the century, maybe the greatest scientific insight since Einstein developed general relativity. So why hasn't anyone heard of Maxwell? Well, the problem is that he died young. At age 48, he had a rare form of abdominal cancer, and the only cure was surgery. But by the time the operation was done, it was too late. He died 2 months later. But before that, he had the satisfaction of seeing his theory put to the ultimate test. The color photograph you've been seeing throughout this video was taken by Maxwell himself. He wanted to prove that color photography was possible, but he needed a complicated setup that didn't exist yet, so he made it himself. First, he created 3 glass plates, each coated with a different type of light-sensitive material. Then he placed an object on one plate, covered it with a dark red filter, and exposed it to light. The red filter made sure that only red light hit the plate, so that any image formed would be really only red. Next, he moved the object to a different plate, changed the filter to green, and took another picture. Finally, he moved the object to the last plate, changed the filter to blue, and took the last picture. After letting the plates develop, he lined them up in order, and the result was the world's first color photograph. It wasn't a pretty picture. It took 8 hours of exposure time, and the resulting image was grainy and washed out. But it proved that color photography was possible and paved the way for today's digital cameras. If that sounds like a complicated experiment, it's because it was. And the reason we can make it look so simple is because of the incredible work by our sponsor, Brilliant. They've created online courses that teach advanced STEM topics in under 15 minutes, so you can learn complex concepts like calculus and large language models on the go. They know how to make learning intimidating subjects approachable and fun. In 1860, the best lecture theatre in Edinburgh was packed to capacity for the debut of Professor James Clerk Maxwell, a new professor of natural philosophy, as physics was then called. He was already well known for his work on color vision and had published several papers on electromagnetism. But he was only 24 years old, and despite his brilliance, many thought he was too young for the post. Nonetheless, the crowd that day was eager to hear him speak. He began by describing how he wanted his course to be like an old man who had seen a lot of life. I want to bring you into the company of great thinkers and great men of science. He went on to explain that he would try to make their studies applicable to everyday life. I want to impress on your minds the truth that it is possible for anyone to be a philosopher. You can all become philosophers. It is not a thing that is confined to a few persons in academical dresses. As he spoke, Maxwell exuded a calm wit. One student later recalled that Maxwell was like a fatherly figure to them. Another said that Maxwell's presence was so calming that one could listen to him talk about the most complicated subject without being confused or alarmed. But Maxwell himself was far from calm. Behind the facade of the model professor, he was fighting one of the worst headaches of his life. Maxwell suffered from migraines, and sometimes the pain was so bad he would curl up on the floor in agony. This particular migraine started a week earlier and was getting worse by the hour. He tried everything he knew to stop the pain, but nothing worked. That day in class, he felt a sharp, sudden pain in the back of his neck. Then his vision flared white. Maxwell cried out and slumped over his desk, unable to speak. The students rushed to his side, but there was nothing they could do. They sent for a doctor and helped Maxwell lie down. Then they waited. Hours passed and the professor did not recover. The students left, giving Maxwell his privacy. When he awoke, he was alone. He lay there for a while, until he could bring himself to get up. Outside, the sun was setting. Maxwell slowly made his way home. He felt weak and shaky. The walk took him 2 hours, but he didn't dare tell anyone he'd been ill. He didn't want to give his students cause for worry. And besides, it would have caused a scandal. The university expected him to be working, not writhing around in pain. Maxwell continued to suffer from migraines for the rest of his life. In his last year in Edinburgh, he wrote a friend, "My head is always aching. My fits of illness are very severe. Oh, that it were otherwise." Maxwell was born on June 13, 1831, in Edinburgh. He was the second son of a wealthy family and had an older sister. When he was 2, the family moved to the country and he grew up roaming the beautiful Scottish moors near their home. From an early age, Maxwell was fascinated by how things worked. At 3, he pulled a rope to see what would happen. When his mother came running, he said, "My heart is giving way." At 8, he discovered he could make a compass needle spin by waving it in front of his eyes. He believed he had discovered a new force of nature and recorded his discovery in a notebook. By 10, Maxwell was a devout Christian, but he also believed science and religion were not mutually exclusive. He later wrote, "Science has advanced our knowledge so far that if we bring its results to bear upon the question of the existence of a deity, the evidence which it affords is just the reverse of that which we should have expected from the mere a priori probabilities of the case. We must either believe that God does not exist, and that this world, with all its train of natural laws and the like, has been produced by chance, or that there is a God whose power is superior to all those laws which he has established. In other words, we must either believe in atheism or in theism." By the time Maxwell was 14, he had mastered math, chemistry, astronomy, and Latin. He entered the University of Edinburgh to study engineering, but soon switched to math and physics. He graduated top of his class and won a prestigious fellowship to the University of Cambridge. There he met some of the brightest scientific minds of the day, including William Hopkins, who became his close friend. Hopkins shared Maxwell's fascination with color, and together they conducted experiments demonstrating that colors were not produced by reflected light, but rather emitted by objects. Maxwell wrote a paper on the subject, which caught the eye of the renowned physicist John Herschel. Maxwell corresponded with Herschel for years, bouncing ideas off each other and discussing science. While in Cambridge, Maxwell met his future wife, Catherine, who was the daughter of the head of the Cavendish Laboratory. They married after Maxwell began his professorship in Edinburgh. Catherine bore him 6 children, but 4 died in infancy. The surviving twins were still infants when Maxwell accepted the chair of natural philosophy at King's College in London. Maxwell struggled through the move, suffering from seasickness on the boat and more migraines once he arrived. But once settled, he threw himself into his work. Maxwell was an avid consumer of knowledge. His mind was like a steel trap. He read voraciously and could recall everything he'd ever learned. He applied this knowledge in his lectures, which covered a wide range of topics, from electricity to mechanics to optics. He was able to draw connections between seemingly disparate fields and show how they were related. He also used his considerable charm to interest his students in science. One student later said, "His lectures were so stimulating and inspiring, they opened up a new world before us and set us thinking along new lines." But Maxwell's interests ranged far beyond his lectures. He loved to discuss a wide range of subjects, from poetry to politics to science. He once remarked, all generalizations are false, including this one. He never shied away from a challenge. He was once asked what he thought about the rings of Saturn. He replied, "I think they are the most beautiful thing in the universe." Later, he explained why. He said, "They are so orderly. They go round and round in perfect circles, never touching each other. It's like a clock. It makes me feel that there is order in the universe." Maxwell studied the rings extensively, and his work laid the foundation for the Voyager missions to Saturn decades later. One of Maxwell's greatest interests was thermodynamics. He was particularly fascinated by the kinetic theory of gases. He used statistical mechanics to describe the behavior of gases and showed that they could be explained as a collection of molecules in random motion. He also developed the Maxwell distribution, which describes the speed of gas molecules in a gas at a given temperature. Maxwell was one of the first to use statistics in physics, a technique that is now ubiquitous in the field. Another area of research for Maxwell was electricity and magnetism. He was familiar with the work of Michael Faraday and others, but he wanted to know why these things happened. He didn't want to just describe the phenomena. He wanted to explain them. So Maxwell set about deriving the laws of electromagnetism from first principles. He used elegant mathematics to show how electricity and magnetism were related. He also showed that electromagnetic waves could travel through a vacuum, contrary to what many physicists believed at the time. His equations elegantly described how electric and magnetic fields interact to create electromagnetic waves that propagate through space at the speed of light. This discovery revolutionized our understanding of the universe. It showed that light was just one type of electromagnetic radiation, and that there were other types that we could unsee, such as radio waves and X-rays. This paved the way for modern technologies such as radar, television, and cell phones. Despite his many accomplishments, Maxwell was a very quiet person. He was often lost in thought and didn't like to draw attention to himself. He was also very shy and didn't like to speak in public. Despite this, he was a beloved teacher and mentor. He cared deeply about his students and took a personal interest in their careers. He was also a generous patron of young women scientists, something that was rare in the 19th century. He encouraged them to pursue their studies and provided them with the resources they needed to succeed. Maxwell died on November 5, 1879, at the age of 48. He had been ill for some time and died of abdominal cancer. He was buried in the churchyard of a small village near Edinburgh. His grave is a simple stone with the inscription, "Beloved but not forgotten." Although Maxwell is not as well known as some of his contemporaries, such as Albert Einstein and Nikola Tesla, he was equally brilliant. His work laid the foundation for many modern technologies, and his contributions to science are immeasurable. There's this one scientific theory that just won't die. It's been dead for 150 years, but scientists still talk about it. That's right. I'm talking about the ether, the stuff that supposedly fills all of space and allows electromagnetic waves to travel. Even though we have no reason to believe it exists, many scientists still find themselves thinking about it. Today, we're going to figure out why. When people talk about the ether today, they're usually referring to the luminiferous ether, but the concept has much older roots. It first appeared in ancient Greece around 500 BC. The Greek philosophers believed that all matter was made of some combination of 4 elements: earth, air, fire, and water. But there was also another substance that they called pneuma, which we would today call ether. They thought this substance was present everywhere, permeating through the other three. Pneuma was believed to be responsible for a lot of things, including the movement of celestial bodies. In fact, the word pneuma originally meant breath, and so the Greeks thought that perhaps the gods used their breath to move the planets across the sky. This might sound a bit silly, but this concept of an all-pervading substance is essentially what we find again in the 17th century with Descartes. He proposed that the universe was filled with an all-pervading substance that he called a vortex. These vortices were made of tiny particles that moved in a helical fashion, carrying energy from one place to another. This energy could then be transferred to the planets, causing them to orbit the sun. Descartes didn't have any direct evidence for this idea. Instead, he came up with it because he wanted to explain how the planets could orbit the sun without violating the law of inertia. You see, according to Descartes, the planets had to be pushed by something in order to keep moving. And since there was nothing in space, like maybe a ball or something, that could push on the planets, he hypothesized that they must be pushed by this invisible substance, his vortex. Descartes' idea was quite influential, and it was until the 1820s that scientists started to generally reject the idea of an invisible substance that filled space, and this is when the next version of the ether was born. Let's go back to the beginning of the 19th century. At that time, physicists knew that light waves traveled at the speed of 186,000 miles per second, but they weren't sure what this wave was actually a wave in. You see, every known wave was a wave in something. Water waves were waves in water, sound waves were waves in air, and so on. But what was the medium that light was a wave in? Well, in 1821, Michael Faraday discovered that electric currents produced magnetic fields. 5 years later, Georg Ohm found that the current through a conductor was directly proportional to the voltage applied to it. And in 1831, Faraday discovered that changing magnetic fields could produce electric currents. These discoveries sparked an explosion of research into electromagnetism. All of a sudden, scientists were realizing that electricity and magnetism were intimately related. Scientists had been studying each of these phenomena for decades, but somehow it took nearly 40 years after the discovery of electromagnetism before someone realized that these two phenomena were related. All of these developments culminated in 1865 when James Clerk Maxwell published his famous set of equations, which we now call Maxwells Equations. Maxwell's equations were a set of 4 equations that described how electric and magnetic fields were generated by charges and currents, and how those fields changed over time. His equations showed that electromagnetic waves would always travel at the speed of light. Now, physicists at the time knew that electromagnetic waves were either the thing that light was made of, or light itself. So Maxwell's equations gave us a lot of insight into the nature of light, but they didn't really say anything about what light was a wave in. That was left somewhat ambiguous. However, most scientists seem to think that Maxwell's equations implied that light was a wave in some kind of medium. After all, they knew that all other waves were waves in some medium. Why should light be any different? And so it was basically just assumed that light was a wave in the luminiferous ether. So now we've got yet another version of the ether. But the problem was, nobody could detect this thing. Throughout the late 1800s, physicists tried and tried to detect this ether, but they never managed to do so. This all changed in 1905 when Albert Einstein published his special theory of relativity. In it, Einstein showed that the laws of physics were the same whether you were at rest or moving at a constant velocity. He also showed that the speed of light was the same no matter how fast you were moving. And so, this seeming contradiction led Einstein to conclude that space and time intertwined in a four-dimensional fabric were relative. Whether you were moving or not depended on your frame of reference. With this new understanding of space and time came the realization that the ether was unnecessary. If the speed of light was always the same, then there was no need for a medium that it was a wave in. But even though Einstein showed that the ether wasn't necessary, he didn't exactly prove that it didn't exist. And so the question of whether or not the ether existed remained open. This is where the story gets weird. Even though Einstein showed that the ether wasn't necessary, he also didn't completely rule it out. And so physicists still had this nagging question in the back of their minds. Did the ether exist or not? What if Maxwell's equations were actually correct and light was a wave in the ether? It wasn't until 1971 that physicists finally put this question to rest. That year, two physicists, Robert Forward and J.A. Wheeler, showed that Maxwell's equations could be modified to work without the ether. That is to say, they showed that Maxwell's equations could work without a background medium. Despite this, modern physicists still often find themselves thinking about the ether. One reason for this is that the ether is a useful mathematical tool. As I mentioned earlier, Maxwell's equations can be modified to work without the ether. But in 1901, a physicist named Alfred Villarta pointed out that you could rewrite those equations in such a way that they looked like they were still describing a wave in a medium. These reformulated equations are known as Villarta's equations. And even though we know that the ether doesn't exist, physicists still often use Villarta's equations because they make it easier to solve certain problems. For example, the equations make it easier to calculate the behavior of electromagnetic waves in certain situations. Another reason physicists continue to think about the ether is that it's just a natural way to think about the world. After all, we've been thinking about light as a wave in some medium for centuries. It's only natural that we would continue to think of light that way even after the ether has been disproven. But perhaps the biggest reason that physicists continue to think about the ether is because of an experiment that was conducted in 1818 by a French physicist named Armand Fizeau. In Fizeau's experiment, Fizeau sent light through a stream of water that was flowing in one direction. He then placed a rotating toothed wheel in the path of the light and measured the change in the interference pattern as the wheel rotated. Fizeau found that the interference pattern changed in a way that could only be explained if light was a wave in a medium. Now, this experiment isn't usually cited as evidence for the ether, mainly because it has some pretty ambiguous results. You see, Fizeau's experiment could be interpreted in a couple of different ways. Some physicists argue that Fizeau's results could be explained if light were a wave in the ether, while others argue that the results could also be explained if light were a particle. In the end, Fizeau's experiment was inconclusive and didn't really settle the debate over the ether. But even so, it's stuck in the minds of physicists ever since. Maybe it's because it's such a simple experiment that anyone can understand, or maybe it's because it's one of the few experiments that was conducted before Einstein's theory of relativity. Whatever the reason, it's clear that Fizeau's experiment has had a lasting impact on our thinking about the ether. But even so, it's interesting to think about what role it might have played in the development of physics. If Descartes was right, and the universe was filled with vortices, or if Newton was right, and gravity was transmitted instantaneously, or if Maxwell was right, and the ether was a real physical medium, the laws of physics would be very different than they are today. I, for one, am glad that none of these hypotheses turned out to be true. But it's also interesting to speculate on what might have been if they were. After weeks of painstaking work, Michelson and Morley completed their interferometer in July of 1887, and while the setup was fairly complex, it's not really rocket science. Light from a common source was split into two beams, which traveled perpendicular to each other before recombining. The key innovation here was the beam splitter, a plate of glass with a half-silvered coating that would reflect half of the light hitting it and transmit the other half. This meant that when the two beams recombined, they interfered either constructively or destructively, depending on which path they took. By rotating the setup, they could change which parts of the pattern were bright and which were dark. This pattern of interference is what makes an interferometer such a useful tool, because it lets us measure tiny changes in the optical path length, the distance light travels through a medium. When the path length changes, the phase of the light wave changes, which affects how it interferes with itself. And if we know the phase of the light wave, then we know how far it has traveled. So the idea behind the Michelson-Morley interferometer was pretty simple. If Earth was moving through a stationary ether, then the light traveling along with it would travel faster than the light going against it. That would mean one arm of the interferometer would be shorter than the other, and they could see a shift in the interference pattern, a fringe shift, which would tell them how fast they were moving through the ether. But when they ran the experiment, they got nothing. Not only did they not see a fringe shift, they saw no fringe shift, zero. They repeated the experiment over and over again, tweaking the setup and improving the measurements, but always got zero. It was an incredibly tense time, like waiting for the results of a pregnancy test, except instead of getting a plus or minus, they got a big, fat zero. There was no way that could be right. They checked everything and double-checked everything, triple-checked everything, but still, the result was always zero. So what did that mean? Well, it meant one of two things. Either the ether didn't exist, or there was some unknown error in their experiment. Now, scientists are trained to be skeptical and question their results, but they are even more trained to believe in the underlying theory. At least, that's how it was in the 19th century. No one wanted to believe the ether wasn't real. It was too fundamental to their understanding of the universe. So most physicists, including Michelson and Morley, tried everything they could to explain away their results. They thought about and tested all kinds of crazy ideas, but none were as painful to watch as the attempts to save the ether using the Lorentz contraction hypothesis. This was a last-ditch effort to explain the null result without abandoning the ether. The idea was that the apparatus itself was somehow being affected by its motion through the ether, preventing it from working properly. The important thing to know is that the Lorentz contraction hypothesis predicted the interferometer should have worked, but only if the apparatus was perfectly aligned with the direction of motion through the ether. If they were moving at an angle to the ether, then the results should have been different. Michelson and Morley had done just that. They'd taken their interferometer and rotated it around to make sure the result was the same, no matter the orientation, which it wasn't. To try to save the ether, they had to unrotate it. They did this by postulating that the very definition of an angle depended on the speed of the observer. That is, the angles of the interferometer itself changed when it moved through the ether. They were chasing their own tails. Now, unfortunately for them, there was a much simpler explanation for why the interferometer didn't work, namely that it didn't. But that wouldn't do at all. So they clung to the Lorentz contraction hypothesis as hard as they could. The idea was that the apparatus was contracting along the direction of motion through the ether, which is why it didn't work properly. That also meant the arms of the interferometer were actually different lengths, which was weird because they were supposed to be equal length. To get around that, they proposed that the source of the light was also contracting. This made sense to them because they knew that the source of the light was emitting waves that were oscillating up and down, and those oscillations would be affected by the motion of the ether just like anything else. So they imagined that the oscillations themselves were contracting, changing the frequency of the light. It was all very complicated, but the bottom line was that they needed the source of the light to be contracting too. And to make that happen, they needed the entire universe to contract. Unfortunately for them, there was a well-known physicist who wasn't having it. Hendrik Lorentz was a brilliant mathematician who helped develop the first version of the Lorentz contraction hypothesis. He saw the flaws in Michelson and Morley's reasoning and wasn't afraid to say so. The two men had very different personalities. Michelson was brash and bombastic and loved the limelight. Their rivalry was legendary. In fact, Lorentz once wrote to his wife after attending a lecture of Michelson's, "I was never more insulted than during the visit to the American Michelson, who likes to talk for an hour and a quarter on the wave theory of light and does not allow anyone to interrupt him. But despite their differences, they respected each other's work and often collaborated on projects." However, when Michelson and Morley published their null result in 1888, Lorentz's objections became impossible to ignore. He pointed out that if the source of the light was contracting, then the whole universe was contracting, which left them with no explanation for why the universe was contracting in the first place. Michelson and Morley's response was to ignore Lorentz and keep trying to save the ether. The final straw came 2 years later when they published a new paper explaining that the reason the ether didn't show up in their experiment was that it was dragged along with the motion of the Earth. It was like trying to swim against the tide. All of their work was undone by the motion of the medium they were trying to measure. At this point, Lorentz decided enough was enough. He returned to his first love, theoretical physics, where he could be sure no one would bother him. Meanwhile, Michelson and Morley continued their feud until Michelson died in 1931. By that time, the ether was a dead theory, and even Lorentz had stopped trying to revive it. Ironically, it was the failure of their experiment that finally put them on the same page. Was a mathematician and physicist who is now best remembered for his contributions to the development of quantum mechanics. However, in the late 19th century, he was one of the leading proponents of the ether. It was a way of thinking about the world. He believed in the absolute truth of mathematics and the laws of nature, and that the purpose of science was to uncover that truth. For him, the Michelson-Morley experiment was a challenge to that way of thinking. When he heard about the null result, he invited Hendrik Lorentz over to his house for dinner to discuss it. Was skeptical of Lorentz's interpretation of the result, which was that the ether was real but stationary. The two men argued for hours over dinner, but neither could convince the other. Meanwhile, went out to the balcony to take a walk. As he paced back and forth, he thought about the implications of the null result. They had to be relative to the observer. It turned physics on its head and shook the foundations of the scientific method, but was the first to see the light. He realized that the null result was a wake-up call, a sign that something was wrong with their understanding of the universe. In the years that followed, Wood championed the idea that the laws of nature were relative. He would argue passionately in salons and lecture halls, trying to convince his colleagues that the null result was proof that the ether didn't exist. But no one listened. It wasn't until Einstein came along and showed them how to quantify the idea that physicists finally understood what had been trying to tell them all along. And that's why physicists say that the ether was a mistake. And if you've been watching my videos, you probably think that I agree. But what did they mean when they said that? Because in 1905, physicists were still talking about the ether. It was an idea that had been around for almost 200 years. So let's go back to the beginning. In the early 1900s, Albert Einstein worked as a patent clerk in Bern, Switzerland. He spent his days examining patent applications and his nights thinking about the universe. One night, he had a thought. Why should we assume that the speed of light is constant? No one had actually measured it. So why not assume that it depended on the motion of the observer, just like all other speeds? After all, how fast something appears to be moving depends on whether you're standing still or whether you're moving too. If I throw a ball toward you at 20 miles per hour, it appears to approach faster than if I throw it while running toward you at 40 miles per hour. This dependence of relative motion seemed perfectly natural to scientists at the time. So why should light be different? Einstein's conclusion was that it isn't. Constancy of c is just a property of nature. It can't be different. This insight led to the development of special relativity and revolutionized our understanding of the universe. Well, except it didn't. You see, Einstein didn't immediately realize how revolutionary his insight was. And in fact, it would be another 10 years before he used it to publish his theory of general relativity. In the meantime, however, the scientific community was slowly coming around to the idea that the speed of light was constant. This might seem surprising. After all, there was plenty of evidence against it, and people's die-hard belief in the ether only grew as more evidence accumulated. But these diehards didn't believe in the ether, for the same reason most people don't believe the weather forecast. They've been burned before, and they're not going to make the same mistake again. Let me explain. Let's go back to 1887, and two American physicists named Albert Michelson and Edward Morley. They wanted to measure the speed of the luminiferous ether by detecting changes in the speed of light as the Earth moved through it. Their experiment was a brilliant design, even though it's also quite complicated. So I'm going to oversimplify it a bit. Instead of shooting a laser straight up into the sky, which would be lost in the atmosphere, they shot it sideways. This way, if the Earth was moving through the ether, they would either gain or lose speed, depending on whether they were moving with or against the flow. They found no difference, which was surprising. When news of their null result reached the Dutch physicist Hendrik Lorentz, he was sure it meant there was something wrong with the experiment. Not only had he predicted a positive result, but he believed in the ether so strongly that he started looking for ways to explain the null result without giving up on the ether. Enter the Lorentz transformations. These equations describe how measurements of space and time change between observers moving relative to each other. This makes them similar to Einstein's later equations of special relativity, except Lorentz didn't use them to abandon the ether. Instead, he used them to adjust the measurements of space and time until the results of the Michelson-Morley experiment matched his predictions. This might sound strange today, but it wasn't all that crazy at the time. Newtonian physics already adjusted for motion with something called the Galilean transformation. These equations are similar to the Lorentz transformations, but they assume that time is absolute and only space changes between observers. The Galilean transformations worked great for most speeds, but as you approached the speed of light, the Lorentz transformations became necessary to accurately describe how measurements changed. Lorentz simply assumed that the ether was stationary relative to the fixed stars, and used the Lorentz transformations to calculate how much the measurements of space and time needed to be adjusted to account for the Earth's motion through it. The issue was that these adjustments seemed unnecessary. Over the next decade, multiple experiments tried and failed to detect the effects of the ether, and many physicists began to wonder if maybe it didn't exist. First, there was the famous physicist George Fitzgerald, who claimed that the null results could be explained if objects contracted in the direction of motion. At first, Lorentz liked this idea, but then he realized that this contraction would have to be exactly the same as what he'd already accounted for in his transformations, so he dropped the idea. However, some people took it in a different direction. Enter Paul Lapacek, a man you've probably never heard of. Lapacek was a high school teacher who corresponded with several well-known scientists, including Lorentz. He suggested that there were actually two types of ether, one that permeated all of space, and a second that filled the interior of matter. This second type of ether would contract when in motion, explaining the null results of the Michelson-Morley experiment. But the weird thing was that the contraction depended on the speed of light. As the speed of light increased, the contraction would eventually become so extreme that it would cancel out the effect of the first type of ether. This meant that the speed of light would appear constant to the observer, and that was exactly what happened in the Michelson-Morley experiment. Now, to be fair, this explanation was completely ad hoc and ignored the original purpose of Lapacek's correspondence, which was to suggest a new theory of gravity. But nevertheless, it made sense to him, and that was all that mattered. Unfortunately, it didn't make any sense to anyone else. The idea of two types of ether was far more complicated than the single ether that everyone else considered, and it also contradicted the known properties of electromagnetism. For these reasons, no one paid much attention to Lapacek's ideas until decades later, after the ether had been completely forgotten. You see, by 1915, Einstein had published his theory of general relativity, which provided an explanation for gravity without the need for an ether. In addition, the British physicist Arthur Stanley Eddington had just confirmed the results of the Michelson-Morley experiment during an eclipse, which seemed to put the final nail in the coffin for the ether. As a result, physicists no longer felt the need to explain the null results of these experiments, and Lapacek's letters were ignored. But here's where things get interesting. Lapacek continued to correspond with Lorentz, but now he was criticizing the foundations of special relativity. Lorentz politely responded that he was wasting his time, but then Lapacek kept sending letter after letter, and Lorentz began to get angry. He accused Lapacek of being a crackpot and told him to stop bothering him. But Lapacek didn't care what anyone else thought. He continued to write about his theories until he died in 1926. Ironically, Lorentz was the one who was wasting his time because Lopatchik was closer to the truth than anyone else at the time. You see, the issue with the ether wasn't that physicists hadn't discovered it yet. It was that the concept of the ether was incompatible with the new ideas of space, time, and reality that had emerged from the scientific revolution. This is why the discovery of special relativity was such a big deal. It forced scientists to reconsider their assumptions about the universe and paved the way for modern physics. This is also why Einstein was so reluctant to abandon the ether. The trouble was that no one else realized it. They saw the ether as a scientific mistake. They couldn't imagine why anyone would believe in something that was so obviously wrong. The ether was invisible and undetectable. It didn't interact with anything, and it didn't even exist outside of the solar system. And if that doesn't sound like the definition of nothing, I don't know what does. Of course, you and I know better. We know that empty space is full of virtual particles and antiparticles that pop in and out of existence. We also know that gravity can affect objects without any physical connection, and quantum entanglement allows particles to influence each other instantaneously across vast distances. All of these phenomena were unimaginable to scientists in the 19th century, which is why they struggled to make sense of the ether. They were trying to fit a round peg in a square hole. Today, we look back on this struggle and laugh at the physicists who clung to the ether. But the truth is that they were the ones who were right. The issue wasn't that they believed in an invisible substance called the ether. It was that they believed in a universe that looked and behaved like the one we live in. It's a foggy day in London. The air is thick with coal smoke from the many fires burning throughout the city, along with everyone else bumping down the uneven road. Your carriage finally reaches its destination and comes to a stop outside of an imposing brick building. Its windows are dark and vacant, save for one set of double doors at the very front. As the coachman rattles the handle, the sound of clopping horseshoes echoes inside. You arrive at the Royal Institution on Christmas Eve, 1839. What will your day be like? Well, let me show you. Your morning begins with a bang as you are awoken in your lodgings to the sound of pounding on the door and shouting for you to get up. You rise from your bed and dress quickly so that you can hurry downstairs for breakfast. Outside, you see the rest of the staff already bustling about, readying the house for the arrival of visitors. You arrive late, but just in time to catch the tail end of a boisterous conversation between two men. One is Professor Faraday, who you have come to assist for the day. The other is an older gentleman with twinkling eyes and a long white beard, who, you soon learn, is Sir Humphry Davy, the president of the Royal Institution. He has spent his career traveling around England, turning on the lights in every major theater and gasworks. Faraday beams at you as he sees you enter the room. His face crinkles at the corners, and his eyes seem to twinkle with mirth. After a hearty breakfast of toast and tea, you depart with Faraday for the nearby spot you know as the Royal Exchange. But today is no ordinary day. It is Christmas Eve, and as you join the crowds spilling out into the street, you realize that everyone has gathered here to watch the grand annual illumination of the Royal Institution Christmas tree. The tree is large, even larger than the elephant at the London Zoo, and decorated with thousands of lights, powered by the brand new electric battery invented by Sir Humphry Davy himself. Soon, a great cheer rises from the crowd as the lights begin to glow. Afterwards, you walk back to the institution hand in hand with Faraday, who points out the newly installed electric arc lamp hanging above the entrance. It is powered by the same principle as the Christmas tree, though much more powerful and far more bright. Finally arriving at the door, you ring the bell and await admittance. When the doors swing open, you step inside and find yourself in a large hall. Directly ahead of you is a polished brass door knocker shaped like a lion's head. Beside it hangs a convex mirror which reflects your image back at you. And if you look closely, you can see the faintest glimmer of candlelight emanating from within the room beyond. As the door opens, you are blinded by the light and fall back. Once your eyes adjust, you realize that you stand inside of a large marble hall. To your right stretches a gallery supported by 6 red marble columns. At the top of the stairs stands a man you recognize as John Henry, the assistant librarian, who smiles and beckons for you to come further inside. To the left of the fireplace, a set of double doors is slightly ajar, allowing you to hear the muffled sounds of hammering and shouting from within. Turning towards the sound, you notice another door set into the wall, beside which stands a simple wooden stool. On it rests a small brass kettle and a pair of tongs. After recovering from your initial shock, you remember your manners and introduce yourself to the others in the room. Though busy with preparations, they are kind enough to welcome you warmly. After hearing about your plans for the day, Sir Humphrey Davy excuses himself to tend to some other business. Faraday, however, insists that you come with him, as he has something to show you. He leads you through a series of rooms until you reach a large, vaulted chamber filled with various pieces of apparatus. In the center of the room sits a tall table covered by a black cloth, upon which rests an assortment of metal spheres and tubes connected by wires. Near it stands a glass case containing a variety of chemicals. Behind it, a small group of people are gathered watching intently, while Faraday adjusts the apparatus. Before you can ask what they are doing, the room suddenly plunges into darkness. Startled, you cry out as a loud hissing noise fills your ears. Then the lights return and you see something that makes you gasp. The spheres begin to spin rapidly on their axes, glowing brightly as they do. Faraday beams at you, pleased with the effect. Soon the demonstration is over and Faraday turns to you. "Would you like to see the steam engine in action?" he asks excitedly. "I believe the assistants are just getting ready to start one up." You agree eagerly and follow him from the room. Down the hall and through an open doorway, you can hear the steady chugging of a small steam engine. As you approach, you see 2 men stoking its firebox. They wear leather aprons and goggles, shielding their eyes from the bright light and heat given off by the flames. Every so often, one of them will reach out and turn a large wheel protruding from the side of the engine. This causes the piston to move back and forth, which is connected to a heavy weight suspended from the ceiling by a rope. One of the assistants looks up and sees you standing there. "Would you care to give it a go?" he asks with a smile. Faraday nods his head and you step forward to try your hand at it. As you turn the wheel, the piston moves faster and faster. The weight rises higher and higher until suddenly the rope snaps and it comes crashing down. You jump back in surprise. Faraday rushes over and kneels beside the fallen weight. "Are you all right?" he asks you, his voice full of concern. You nod your head, still shaken by the sudden accident. Faraday helps you to your feet and dusts you off. "Let us leave them to their cleaning," he says, leading you away from the commotion. You walk together in silence for a few moments before Faraday speaks again. "Do not worry," he says. The accidents are all part of the fun. Just remember, no experiment, no discovery. You ponder his words as you continue on your way. It seems that the rest of the morning will be taken up by preparing for the afternoon's lecture, so you take it upon yourself to explore the building. Wandering through the halls, you discover several interesting things. First, there are books everywhere, lining the shelves from floor to ceiling. You open one at random and find that it contains detailed notes and diagrams on various experiments. Tucked behind it is a small notebook with entries detailing everything from chemical formulas to the price of coal. Further down the hall, you hear the sound of hammers and nails being driven into wood. Peeking around the corner, you see a man using a mallet to shape a piece of metal. Another sits at a workbench, sharpening a tool while humming a tune. And in the corner, a boy sweeps up scraps of metal and wood. You continue on until you reach a large room dominated by a large stone fireplace. Above it hangs a portrait of a stern-looking man with a white beard. Next to it, mounted on the wall, is a collection of instruments, including a thermometer, barometer, and hygrometer. As you examine them, you wonder what experiments might have been performed here. Next, you visit the kitchen where you meet the cook. She is a stout woman with rosy cheeks and flour-dusted hands. She gives you a warm smile and invites you to watch her prepare lunch for the staff. While she chops vegetables, stirs pots, and tosses pancakes, you help set the table and pour the tea. Finally, it is time for lunch. You sit down with the others and enjoy a meal of bread, cheese, and ale. Afterwards, you return to the main hall and decide to climb the grand staircase. At the top, you can look down on the room below and see the staff scurrying about, readying everything for the afternoon's event. You hear the sound of children's voices echoing from within the lecture room. Curious, you open the door and peek inside. You see Faraday standing on a chair before a group of attentive children. He is holding a small battery in his hand and explaining how it works. The children are wide-eyed with wonder as he demonstrates his invention. Just after midday, as the crowds were assembling outside the lecture room of the Royal Institution in London, two men entered quietly. One of them, an eminent scientist, had just come from a morning at his club debating the merits of phlogiston theory with some colleagues. It was 1774, and that theory proposed that all combustible bodies contained this mysterious substance. To explain how things burned, when they lost enough of this substance, they would burst into flames. As he took his seat in the front row, the other man, a wealthy connoisseur of fine art, was thinking about the tea service he'd purchased at the shop recently. It was made of crystal. He was hoping that the afternoon would be soporific and that he'd be able to get in a good nap before tea. Both men were in for a surprise. This is one day at the Royal Institution. This is Regency tea break. It's me. And today we are having tea in the lecture room of the Royal Institution in London. It's the afternoon of December the 9th, 1774. And we have just heard a most alarming report from our esteemed colleague at the club about an explosion of some kind in Newcastle. Some people think it may have been gunpowder, others that it might have been a gas. We don't know which. But now it is time for tea. We will begin with the crystal cups. Now, these were bought by one of our members from a well-known shop recently, and we are most grateful to him for providing them. They are filled with the proper tea, of course, from our own blend. Our tea comes from a very special garden near the hills of Assam, where the first flush of the year is picked in February. because they pick only the unopened buds, not the full-blown flowers, which would make the tea bitter. And what a glorious brew it is. And our cakes today are made with the proper amount of butter, not too much, not too little, and exactly the right consistency. The fruit cake is packed with raisins and currants, and the light cake is flavored with lemon peel. And we are most fortunate that our caterers were able to provide us with the proper scones, baked in the old-fashioned way, which means, yes, they do have a wee bit of fat in them. These are hard to find now, but they are absolutely the proper thing. And if you want to see how they are done, we have a most instructive pamphlet on the subject, which was published in 1824, and which is still available. When we burn wood, its weight decreases. This can only be because the phlogiston has escaped, and so all bodies contain phlogiston, and it escapes when they are heated, until, when it is all gone, the body bursts into flames. But there is a problem, and our esteemed member, who was at the club this morning, tells us that in some experiments with metals, the apparent loss of weight cannot be accounted for by any quantity of phlogiston, and that is a puzzle. I say apparent loss of weight because you see, it is true that the bodies increase in weight when they are burned. That is to say, they gain weight, but here they lose weight. Is this because the phlogiston is coming back? No, no, no. You see, we know that is not possible. She goes quickly to a chair and curtsies deeply to a lady seated there. She is then beckoned to a table by another lady and takes a seat among a group of gentlemen. A most improper scene. A lady should not be in the gallery at all, much less in the front row. Such indelicacy. But it is true. This is London, and a plague of women are attending lectures at the Royal Institution. And this is a most dangerous thing to have in the lecture room, since, if the slightest shock were to reach it, it would explode. There is nothing like witnessing a destabilizer in action to remind one of the reality of the forces that our chemists are investigating. As the ladies sneak into the lecture room, unnoticed, the conversation around the table is becoming heated. Then how is it that metals, in some circumstances, lose weight when burned? Can it be that different substances lose their phlogiston in different ways? Perhaps. Could there be different kinds of phlogiston? Oh, what a preposterous notion. Only one kind of phlogiston can exist. If there were different kinds, why would they all go in the same direction? And then what would happen if one encountered the other? By the great fire of brimstone, you are quite right. How could anyone have thought such a thing? Let us change the subject. If you want to hear more about the combustible substance known as phlogiston, we suggest you take a look at our past videos on the subject. We trust they will prove diverting, and you will see a most delicate film of nitroglycerin appear here. We need only touch it with a red-hot musket ball. Will you look but do not touch? Oh look, the film is already becoming thicker. It is growing. Must touch it with the musket ball. Do not touch. Come away, I say. Yes, the film is thickening. Look at that, and there is a crack. Oh dear me, a leak. Quickly, bring the extinguisher. Stop the leak. And yet, it still grows. And now I must stop it with this block of wood. It will burst. Gentlemen, stand back. Good heavens, it has burst. Ah, now there is a most disagreeable smell, like the fumes of the East India Company's rum. Has something displeased him about the demonstration? Not at all. No, no. I find he is worried about the behavior of some of our female members. Do you see that box over there? Yes, that one with the silk curtains. I believe there are 2 women hiding in there, and that box beside it has 3. And those 2 over there, they seem to have fallen asleep. I fear it isn't safe. should we not rouse them? No, no, let them sleep. They are not doing any harm. What is it? You can't make it out, can you? Well, look closely. Look closely, I say. What is it? Why, she is listening intently to every word and every experiment. That is proper feminine decorum. No, no, she is the sister of the great Sir William Herschel, discoverer of the planet Uranus. And she has been attending these lectures because she wishes to understand the science upon which her brother's discoveries are founded. Indeed, when her brother first came to England from Hanover, it was she who supported him and enabled him to buy his first telescope. And she is herself a musician of some accomplishment, and her services to music are commemorated in a medal that was presented to her by subscription in 1826. Most women are like my wife and your wife. They belong in the home and should not be out in public, least of all in a place like this. I am sure that your wife would agree with me. Would you not agree, my lady? Your Majesty, what an unexpected pleasure. It is my duty to tell you that your Majesty's attendance does us the greatest honor. Please do not trouble yourself about those ladies. You see, they are merely here to learn. They do not wish to distract from the discourse. In fact, we are most fortunate in having such discreet admirers of science in our midst. Here, ladies are most welcome. Are you not glad of it, Mrs. Siddons? And you, Miss Reynolds? I am very glad to have such distinguished patrons of the arts and sciences among my audience. And I know you will agree with me that these ladies are a credit to their sex. It's 1846, and you're about to spend a day at the Royal Institution with me. Come along. Our first stop is the lecture theater, where an experimental scientist, John Henry Tyndall, is about to start his afternoon demonstration. Tyndall has been in hot water recently after publishing some results from his experiments into the nature of light and dust, which have upset some religious people. The reason? His suggestion that the beams of light he has been observing in his darkened laboratory, which are produced by particles of dust suspended in sunlight, might actually be atoms of light, or, in other words, photons. While this idea will come to be known as Tyndall scattering, the name given by Lord Rayleigh nearly 2 decades later, it is not going down well with everyone here in London. And before Tyndall appears, there is a smattering of boos and some hissing from the audience. It doesn't help that the title of his lecture is on the physical and philosophical limits of the microscope, because that sounds like he's about to tell everyone why God doesn't need microscopes to see the 7-eyed monster in the lady's stocking or the devil in the pudding. You know what I mean? Those pesky heathens. Once Tyndall emerges from behind his Faraday cage contraption carrying a wide-beamed laser and a pair of tweezers, any lingering hostility evaporates. After all, no one can stay angry when someone is wielding a light weapon. The audience, which includes the Duke of Devonshire, future Prime Minister Lord Derby, and scientist Michael Faraday, are treated to a demonstration of Tyndall's famous scattering experiments, and the beam is split into different colors by a prism. If the invisible is made visible, then the unseen world of atoms and molecules suddenly seems less scary and more wondrous, and the religious are appeased when Tyndall assures them that these particles are not the same as those making up the human body, so they don't turn into bread when they eat them. All well that ends well. Meanwhile, back in the lab, we have our next engagement, but we'll have to hurry if we want to make it in time for the start of the second lecture. There's a problem with the vacuum pump, the piece of equipment used to create a vacuum inside the demonstration apparatus, and, unfortunately, there isn't a spare at hand. so Tyndall needs a quick replacement. He chooses a syringe and some tubing, and after attaching it to the apparatus, gives the handle a few vigorous pumps. Unfortunately, though, the makeshift replacement isn't up to the job, and a small amount of air remains inside the device. Tyndall is undeterred, though, and plunges a red-hot musket ball into the tube. No one in the audience can see inside the tube, because the rest of it is surrounded by a black cloth screen. But when Tyndall removes the cloth after the musket ball has finished fizzing, it's clear that the air in the tube has become luminous, glowing with a beautiful blue light. A little bit of tinkering reveals that the glow is coming from a small hole near the top of the tube. And so Tyndall concludes that the partial vacuum he has created has caused the air molecules to lose their elasticity and is able to pass through the small hole. To prove this, he tries again with a different apparatus, this time with a piece of oiled paper placed over the top of the tube. This time the tube fills with a bright yellow light, and when he removes the oiled paper, the end is quite clearly glowing. It looks a lot like the Northern Lights. Later experiments show that the color depends on the size of the hole and the pressure of the air, suggesting that it's being emitted by molecules colliding with each other inside the tube. And although Tyndall doesn't know it yet, this phenomenon will eventually be named the Tyndall effect after him. Next, it's time for some interactive questions and answers. Tonight is one of the most popular slots in the Royal Institutions program, allowing members of the audience to ask questions on any scientific topic. Unlike today, though, when the same questions are asked every week and the answers are thoroughly rehearsed. These sessions are truly unscripted and therefore unpredictable. The aristocratic audience members take full advantage of this opportunity to ask about topics that genuinely interest them. One nobleman wonders if electricity can cure gout. Another wants to know how quickly cabbages can rot if the air contains only one single molecule of carbonic acid. And someone else wants to know whether crocodiles could be domesticated. But the real highlight comes when a member of the audience asks Tyndall if he thinks it possible to construct a boat that will float on air. This brings a smile to Tyndall's face, and he launches into an explanation of Archimedes' principle, the buoyant force that causes objects to float on water. But he doesn't stop there. Instead, he makes a small boat from a sheet of paper and a cork and demonstrates that it will indeed float on a beam of light. The audience, including the Duke of Devonshire, are invited to step onto the platform to try it for themselves. But when the Duke's wife tries to steer the boat using 2 knitting needles like oars, she accidentally knocks it over, and Tyndall steps in just in the nick of time to save it from sinking. After such an exciting evening, you might think that would be enough for one day. But it's time to meet William Prout, who has just finished his own evening lecture on the subject of electrolysis, and it's time for a quick tour of his laboratory. Unfortunately, though, you've just missed something rather important. As soon as Prout entered the lecture room, he was presented with a sealed envelope containing the results of a vote that had just taken place among the members of the Royal Institution. In it, he discovered that he had just been elected a fellow, but you didn't see it, so let's move on quickly. And oh look, while you were gawping at the pretty colored flames in the Bunsen burner, someone has just popped the question. That's right, after 10 years together, William Prout has just proposed to his longtime collaborator, Marianne Bell, who has just said yes. Everyone is very happy, especially when Prout pulls out a ring from his pocket to show the assembled guests. Congratulations are in order. Now, if you want to see the results of Prout's research published in a book, then you won't have to wait long. Just head over to the printing press room, where a new invention called a steam press is just being put into operation. This machine, invented by J.F. Reproduca, uses steam power to drive a printing press, making it much faster than anything available at the time. The operator types a galley of text and images, which is then cast in metal type. The entire page is inked and stamped onto a sheet of paper in a single pass, and the whole thing takes less than 2 minutes. From there, the sheets are transported by a conveyor belt to another room where they are cut and folded. Once they're bound, the books are loaded onto a cart and taken to the delivery room. Here, a team led by the ever-reliable Edmund Custis is just loading a pile of books onto a steamboat, which is chugging merrily nearby. Once the books are secured, the rope holding the cart is released, and the steamboat chugs off down the canal towards its destination. Some of the books are destined for the shelves of London bookshops, while others will be sent to a bookseller in Edinburgh, which may explain why the cover of one of the books is inscribed for a customer in Scotland. Now, unless you can get on the next steamboat yourself, there's nothing to do but sit tight and wait for your copy to arrive in the post. It's the only way to get a book on electricity by William Prout, one of the founders of the Royal Institution, delivered to your door without having to leave London. Until next time, our voyage through the earliest physics laboratories draws to a quiet close. We've felt the teeth of our first electric shocks, polished glass so thin that a careless hand meant ruin, and inhaled the faint, toxic vapor of mercury. We stood beside Maxwell as he listened in equations for light's secret melody. We watched the scientific world cling to the ether, only to have it slip through their fingers, and we sat in hushed awe as Faraday and his successors turned dry demonstrations into grand theater for high society. These dusty benches and flickering lamps, these coils and coils of copper, were the crucibles in which our modern understanding was forged. They remind us that science is born from patience, precision, and a willingness to face the unknowns, to embrace sparks, both literal and metaphorical. As you return to your own world, carry with you the ghostly hum of those first laboratories and the wonder they pursued. For every device you touch, every beam of light you see, traces its origins to these humble workshops. And though the tools have changed, the spirit remains, a restless curiosity, ever ready to illuminate the unseen. Good night, and may tomorrow's sparks guide you ever closer to understanding.